Great, well thanks everybody. So I thought yesterday was fantastic, went really well. So for today, we've got some really interesting stuff, quite a bit on the science and research into alkaptonuria. So we'll start off with Juliet, who's lecturer of anatomy at the University of Liverpool, who's going to be talking to us about the research that she's been doing into AKU, which is going to be fantastic. After that, we'll have Brendan, who'll talk about the tyrosine inhibitors that I mentioned yesterday. Then we have Nutricia doing an update on their latest products and services. And then there'll be two parallel sessions, one on Pilates and one will be on AKU in children, which will be facilitated by Jess, which Ranga will be talking, and also we'll have Claire. Then some water exercises, and then to finish, we'll have a 1 hour history of AKU by Ranga. So Juliet, I'll hand over to you. Oh, is there a fire alarm slide again? No fire alarms today. Well, no tests.
Okay, so hopefully this is a good distance from the microphone. So good morning. It's a privilege to be here and speak to you all today. I really enjoyed yesterday. So some of you know me, but I'm Juliet, and I've got a slide on about me in a moment. But I'm going to give you an overview of the research that we're doing as a group at the University of Liverpool. So who am I? So I am a lecturer of anatomy. That's kind of half of my job. And then the other half of my job, I'm a researcher, and my interest is alkaptonuria. And for anyone who loves animals, I'm a cat person, probably not a dog person. So a bit of my background. So I moved to Liverpool in 2012 to study my undergraduate degree in anatomy and human biology. So that's where my teaching interest came from. And then I stayed to do a master's year. I then embarked on my PhD in 2016. You can see a picture of my supervisory team there. So hopefully you'll recognise Jim, Ranga, and then my other supervisor, George Bigarios, who can't be here today. So this was really my introduction into AKU, and my PhD was based on it. And the three sort of big things that I did in my PhD was characterise our new mouse model of alkaptonuria that George made for us. Did some nice experiments showing that the liver is really the crucial organ for HDD activity in the body. And then also did some preliminary work that's really led into sort of Brendan's work, which he's going to present next, showing that dietary restriction of protein is effective at reducing serum tyrosine in mice that we treat with Nitisinone. So after my PhD, which kind of coincided with the end of the pandemic, I took a teaching lectureship at a small town called Ormskirk nearby in anatomy, and I loved it. I really was missing the research side of my job, and then I was fortunate to get a position back at Liverpool last July as a lecturer of anatomy again, but with a significant part of my contract dedicated to research. So I'm glad to be doing AKU research again. So I thought I'd begin with a sort of overview of the AKU research group at the University of Liverpool. There are probably a few more people, but this is the main core of us. So at the top here, we're kind of the people leading the AKU research at the moment. So we have Professor George Bigarios. He's an expert in mouse models, cartilage and osteoarthritis, and more recently he's leading the work on gene therapy. We have myself, so I research AKU and also osteoarthritis, and I'm kind of interested in the pigmentation that's happening in AKU. We then have Brendan, so he's speaking after me, so I won't say too much, but he brings a lot of expertise in metabolomics, so looking at the sort of chemicals that are present in AKU, and also looking at the tyrosine. And then we have another professor who's a biological chemist. I can't even begin to understand some of the things that they do, but he's helping us look at the sort of chemical structure of what is pigment, basically. We then have two long-standing sort of postdoctoral researchers. Some of you might have seen them before, Hazel and Pete. And then within the group at the moment, we've got 5 PhD students, and they're all working on different topics, as you can see there. So there really is a nice big group of us. We, of course, work very closely with Ranga and Jim, who most of you probably know. We work closely with the NAC, the Royal. We have many collaborators at different institutions. And we also work with you guys loosely as well. We have lots of your patient samples, from joints to plasmas to urine samples, and they come in very handy. So that's a nice overview. So I'm not going to go into this slide too much because I think this is what Ranga's talk will be later, and I found this on the AKU website, and it's sort of a big summary up to 2020 of all of the big milestones in AKU research. And I think you can see that as you progress towards 2020, a lot of the research really was driven towards nitisinone, showing that it was effective in the mouse, and then leading on to the clinical trials that Nick described to us yesterday, and also some nice research looking at pigmentation of cartilage. But now that nitisinone is licensed, I think this has given us much more opportunity to expand our research into lots of other areas of AKU. So as a research group at the university, these are sort of our 5 main priorities at the moment. Nick mentioned quite a few of these yesterday. So Brendan's really focusing on nitisinone-induced tyrosinemia, and he'll tell you about that next. And then long term, we are interested in gene therapy, but that's going to take a little bit longer. Ongoing, we're looking at ochronosis, tissue degeneration, and the chemical structure of the pigmentation. And I think a new area for us really is looking at the role of oxidative stress in AKU as well. So what effect does HGA, tyrosine, and pigment have on the body? My area at the moment is mainly focused on ochronosis, so I'll tell you a little bit about that as well. So just wanted to highlight, Nick mentioned our AKU mouse models yesterday, and I just wanted to highlight how important they are for our research. We don't do animal work lightly, it's always with a goal, and we have to have reason for doing that. So we use them to understand the biology of AKU, and we also use them for preclinical testing of various treatments, trying to find targets and different interventions. So they are super helpful. So I'm just going to give you an overview of what our mouse models can offer us. So just like people with alkaptonuria, our mice produce urine and it turns black. You can see some black urine there from a cage. It's always reassuring to see that in our cage, so we know our mice still have AKU. And then just like in you guys, we can measure the HGA that's present in the urine and the blood, and you can see compared to non-AKU mice, the HGA is elevated, and we use exactly the same methods to measure this that we do for patient samples over in the Royal. We can look for pigmentation in the mouse model. Now the mouse models don't get such as an extreme pigmentation that we see in humans. So when we look at human joints, we can see that they're black. When we take out the mouse joints, we can't actually see anything unless we look at the microscopic level. So we have to take like really, really thin tissue slices. We stain the joint. So this is an example of a piece of cartilage from a mouse knee joint. And then we look at it with a microscope, and then we start to see the presence of, see these little dark spots here of pigmentation present that you can't see in a non-AKU mouse. It's kind of good and bad that they don't get like a strong AKU phenotype in the joints. It does allow us to actually look at the very early changes that are happening in the joint that we can't look at in you guys. We can't come along and take a chunk of your sort of normal knee joint. I don't think any of you would like that. So they are really helpful. And then importantly, our AKU mouse responds to nitisinone. So when we give them nitisinone, we just put it in their drinking water. The HGA goes down, and then we get that huge 10-fold increase in tyrosine. And that's a really important preclinical model for us at the moment. Brendan uses it quite a lot when he's looking at strategies to reduce tyrosine. So this is the last slide on the mouse model, and we've also used this mouse to sort of look and confirm where that HGD enzyme is located in the body. We looked at lots of different tissues, and we found it in the liver and the kidney, which wasn't really a surprise, but it was nice to confirm. And then we also did a series of experiments that, it's a bit cut off here, but basically showing us that the HGD in the liver is the most important location for HGD, and that for a future gene therapy, we need to put expression back in the liver. If we put it back in the kidney, it can't get rid of the HGA by itself, so the liver is the main target for that. For the rest of the talk, I'm just going to show a little bit of the research that we're doing to look at tissue pigmentation. We have much, much more, and I'm happy to chat to anybody today. I'll be around all day. So I'm just going to give you a sort of general overview of some of the things that we've found from AKU tissues. So I have got some photos of AKU tissue as well, so if anyone's a bit squeamish, you might not want to look. Okay, so what do we know? despite nitisinone treatment, ochronosis and tissue degeneration is still an issue for many people with AKU. So it is something we're still really keen to have a look at. Sorry, I can't stop the feedback. So what do we know? We know that ochronosis affects cartilage more than any tissue in the body, but we don't actually know why it's so attracted to this tissue. And we also know the ligaments, tendons, and the heart valves are also affected. And this is something we can't study in our AKU mice, actually. They don't develop pigmentation in these tissues. So the human tissue does come in really helpful. So what are our main questions going forward? Kind of going back to basics, actually. We're still trying to understand the exact chemical composition of the HGA-derived pigment. We know it comes from this really small little molecule, but we don't actually know the exact composition of the pigmentation and how it changes chemically. And then also what it binds to or attaches to within the tissue. We're not entirely sure. So within cartilage, for example, you have cells, and there are hundreds and hundreds of different molecules that surround your cells, and we don't quite know which of those molecules that the pigment is binding to. And then I think importantly, once the pigment establishes itself within a tissue, we don't really understand how it then causes tissue degeneration. So we're really keen to understand the mechanism of that, so how it leads to joint osteoarthritis, tendon and ligament rupture, and heart valve stenosis. So if we have an ultimate goal of understanding, could we remove pigment from tissue, we really need to understand the basics first. And then I think more widely, understanding the accelerated joint destruction we see in AKU may also benefit other disorders such as general osteoarthritis in the rest of the population. So how can we investigate tissue pigmentation? This is just some of the tools that we have. So I mentioned we have our AKU mice, so we know they have high HGA, and we know they have pigment, but it's only mild, so that is a downside. And then the other sort of disadvantage of our mice is that they don't develop an osteoarthritis, so we can't study that process in the mouse model. So what we've done, we've recently acquired a new mouse model, and it's a mouse model that naturally develops osteoarthritis, so we're really keen to combine the phenotype of this osteoarthritis mouse with AKU to help us study the changes in AKU specifically. I mentioned earlier that we're interested recently in oxidative stress, and we think this maybe has a role in the pigmentation process. So George in our lab has recently made us a new mouse model that has both AKU and increased oxidative stress. So we want to see if it makes the AKU condition worse, and if it does so, how does it do that? So hopefully we can learn something there. So I've talked a lot about mice, but we do also have other tools available in the lab. We're quite keen to do a lot of work sort of in the lab using cells. So these are cell lines that we just grow in the lab, and you can just buy them from anywhere. So we're specifically looking at cartilage cells, and we can make them AKU by simply adding the HGA molecule to them, and they form a pigment. So we're really keen to use these models as well to understand some of the basic biology of what HGA and pigment is doing to the cells. And then I mentioned the study of human tissue as well. That's super important to us, and we thank any of you who donate your joints or even their bodies to us. It's really, really valuable. So for the rest of the talk, I'm just going to show you some highlights from human tissues. This really is a gift that we get samples from you, so I just thought I'd highlight some of those. Okay, so here's some highlights. So this is work that began about 15 years ago with Jim and some of the students he's had in the past, from looking at donated AKU joints. So there's this sort of conception in sort of general osteoarthritis that cartilage wears from the top down to the bottom in a sort of top-down manner, wearing away so that you get to the bone. And what we actually see in AKU, so here's a cross-section through a joint, here's the bone, here's the cartilage. We actually see the pigment developing in the really deep layer and spreading upwards and then causing joint degeneration. So we think this is kind of quite unusual, quite different, and is something we're really keen to understand. Why on earth does this HGA pigment target such an unusual tissue in such a specific place?
Juliet, could you just stand in closer to the mic?
Closer, is that better? We'll see. And then we know that once pigment fills the cartilage, it turns black, and then it causes degeneration. So over here, I think some of you have seen this image before. This is an AKU shoulder joint. If you were to see a normal non-AKU joint, you should have a really nice white glossy surface. So the cartilage in this person would have turned black, and it's actually eroded away all the way down to the bone. So we can't actually see the black cartilage anymore. So this must have been very painful. We've also found some really other interesting features by studying AKU in joints. So we had an AKU hip joint, I think from somebody in this room, probably. This is a really, really interesting finding. So this particular hip joint actually had loads of intact cartilage that was causing quite a bit of pain. Professor Alan Boyd in London did some really, really nice imaging, high-resolution imaging of this joint. We found these intriguing, really spiky, high-density mineralized protrusions coming up from the bone and sort of spiking into the cartilage from below. And we think this probably has a role in the pathogenesis of AKU. But they were actually since found in general osteoarthritis as well. So by studying AKU, we found something that we didn't know before. So again, this was work that Jim led probably about 10 years ago. So the rest of the images I'm going to show is some work that I've done recently. So I quite like looking at the joints with histology. It's really pretty, but we also get quite a nice insight. So here is a piece of cartilage, and I hope you can just about see we've got some pigmentation beginning in the deep layer there. And then what we can do, we can slice this into the really thin slices. It's about 0.005 of a millimeter. Stain it, and then we can look at it with the microscope. So this is what we can see here. So it's just like this little region here. So at the bottom, this really dark pink, that's bone. Then we have cartilage on the top, and the cartilage is actually divided into two layers. So we have sort of a middle layer here that's cartilage that is calcified, and then we have a layer on the top which is normal non-calcified cartilage. And in AKU, for some reason, the pigmentation attacks the cells in the calcified layer, and we don't know why. It's super intriguing, it's such a puzzle, and it's something we really, really want to understand. So we know that this will then spread, though, later on to encompass the entire cartilage matrix and lead to degeneration. So we also find that pigmentation, when we look across a body, so these tissues are from one person, that it's really not uniform. So different cartilages in different places pigment at different rates, and that's also something that we want to determine why it does this. We think it could be lots of factors, such as what is the tissue made of, perhaps it's loading of the tissue, lots of different things. But I think you can see here that this is black. This cartilage here looks pretty non-pigmented, actually. And we see the same in tendons and ligaments as well. So on the left, there's an example of a healthy-looking non-pigmented tendon. And then on the right, we have a tendon here. So tendons connect your muscles to your bones to help you move. We have quite a diseased, quite a thickened, pigmented tendon that also had quite a lot of calcification. And I think tendons and ligaments, we haven't paid that much attention to them, and it's something we really want to look at because it really must affect function of movement and how you move around. So I just want to take the opportunity as well. These tissues were from one particular person who bravely donated their body to the University of Liverpool to allow us to look at the tissues across the body, and we can't thank that donor enough and her family. It's such a valuable insight, and it was a privilege, honestly, to work on this project. My last slide of tissues. We also looked at the cardiovascular system. We find that some of the large arteries become pigmented, so within the blood vessel wall, but the veins do not. And again, we don't know why. They have a similar structure, similar function. So why are they pigmented and others aren't? I think if we can understand these things, it will just give us so much, such a deeper understanding of how pigmentation is occurring. And then also, we had a chance to look at a heart valve as well. You can see it's pigmented, and it was also quite calcified. So again, something we want to look at. So I hope you can see that we have learned a lot through the study of tissue. We're beginning to understand how pigmentation attacks the body, but really we do have quite a lot that we still need to learn. So cartilage will always be a major focus because it causes such devastating osteoarthritis, but I'm really keen to look at other tissues such as the tendons and ligaments, as I mentioned, the heart valves, and also the spine. Some of you may know Dr. Mariusz Kujawa from Poland. He's recently come on board as a collaborator with me, and we're really interested in looking at the changes in the spine over time through all of the images that you guys have done at the NAC. So we're really trying to understand that. And hopefully you can appreciate that if we want to look at new sort of targeted treatments, different ones, we really need to understand the disease mechanism more. And then hopefully anything that we learn from AKU could also benefit the wider population as well. So that honestly was such a whirlwind tour of some of the research that I do. So thank you for listening, and I'm happy to take any questions, and I'll be around all day as well.
So thank you to Juliet for setting the scene very nicely and introducing the kind of the wider environment of research here into AKU in Liverpool. So I'm Brendan, and I'm going to talk about specifically about tyrosinemia and some of the research that we've been doing here in Liverpool into potential new therapies to address this unmet need. So my research career is probably a little bit more meandering than Juliet's. I've studied at a few different places, few different areas of scientific research. I started working on AKU in 2015, so I joined the lab here in Liverpool to work on AKU to do my PhD. That was supervised by Ranga and Jim. And I've stayed here because it's a great research environment. I love working on AKU research, and gradually I've become more and more independent thanks to funding from the AKU Society. And now I'm at the point where I'm able to lead some of these exciting new research projects into AKU. So I work closely with Juliet and the rest of the team here in Liverpool with our clinical collaborators. My main area of expertise is analytical chemistry, so various different methods of quantifying and measuring different molecules that are of interest to us in AKU. So HGA, tyrosine, the whole pathway. And really this is the cornerstone that enables me to work in various different areas of research in AKU. So Juliet introduced these really nicely. Various areas. I'm going to talk today about tyrosinemia because it's the of major interest to really the here and now of AKU. But this is just to really highlight that we have many different collaborations with lots of different groups within academia, sort of globally. We have lots of industrial collaborations as well, so we're really using different areas of expertise to inform our research here. And also, again, thanks to funding from the AKU Society, we also have some really bright PhD students who will hopefully go on to be future leaders in their respective areas as well. So we're in a great position here in Liverpool. I'm going to talk today about tyrosinemia, so I promise this is the only pathway slide of this kind. You're probably sick to death of it already. But this is just really to introduce tyrosinemia. So in patients that are on nitisinone, it causes a block at this part in the pathway. So it's a great therapy for preventing the formation of HGA, as we all know. But unfortunately, a knock-on effect of that is that there are an increase in metabolites upstream in the pathway. And the main concern is around tyrosine. So tyrosine increases in the circulation in concentration. And the problem isn't that tyrosine is present and at high concentration in the blood per se. When it's in the circulation, it has access to various tissues throughout the body. And it's the accumulation of tyrosine in these tissues that is really the concern. So I know it's been mentioned yesterday that corneal keratopathy, so tyrosine crystallizes in the eye, in the cornea, and it can cause this, this sort of condensation, precipitation of tyrosine, because it's not very soluble, and this causes, you know, various different symptoms that really we don't want to see. Juliet mentioned our mouse model, so we've done research here on our AKU mice and when we give them nitisinone, we see tyrosine increases in the blood in the same way. And we've also shown that tyrosine accumulates in the brain as well in these mice. The consequences of this are not really known, but tyrosine's a really important molecule for synthesis of other important molecules like dopamine. So it is a concern that we have such high concentrations of tyrosine in the brain. So we're really trying to understand what the full consequences of this are, and how we can prevent it from happening in the first place. So Claire, in her talk yesterday, gave a really nice kind of overview of different dietary interventions, and also the basics of how we get from tyrosine that is, you know, a part of many of the different types of protein that we usually eat, how we get from tyrosine in food to tyrosine into the blood. So just to recap some of this, so tyrosine is an amino acid. Proteins are composed of various different amino acids, of which tyrosine is one. So when we see a protein, we can think of it like a long chain of different amino acids. Some of these will be tyrosine, but there will be other amino acids as well. And as we consume protein, and it goes down the GI tract through the digestive system, it's exposed to various different enzymes. And the result is that this long chain of amino acids are broken down into much smaller molecules. So we have single amino acids, we have 3s and 2s, and it's in this form that we have absorption of amino acids into the blood. So some of these are tyrosine. We get tyrosine in different forms, and it's in these much smaller molecules that we absorb tyrosine from the gut. So there are two main, I've just mentioned the gut and the diet, which is one major source of tyrosine and how it enters the blood. There's another major organ as well, so this is how absorption of amino acids occurs from the diet. It enters the gut, it crosses a lining of cells and enters the bloodstream. We also have the kidney. So the kidney is where many different molecules are filtered out of the blood. So waste products of metabolism, for example, things that the body doesn't need. The kidney does a great job of filtering those out, and if they're not needed, they're excreted in the urine. Amino acids, we know they're needed for lots of different processes in the body, for protein buildup, for example. So the kidney likes to do what we call reabsorption of amino acids. So it reclaims the amino acids that would otherwise be excreted in the urine. It stops that from happening because they're useful. It diverts it back into the blood. So this is what we call reabsorption. So in these processes, there's a lot more going on. It's not simply the case that tyrosine floats across these different organs into the blood. It's a much more sophisticated and tightly controlled mechanism. And in order to do this, amino acids, including tyrosine, must cross these biological membranes. If we didn't have these membranes, it would be total chaos. We'd have molecules that can come in and out of the blood. Things we don't want in the blood would be free to enter, so it wouldn't be a great system at all. So looking at this in a bit more detail, I'm going to be talking for the rest of the presentation about amino acid transport. So it's really fundamental that we understand how tyrosine is transported in and out of the blood. And what we have, so we have linings within these different organs that prevent things from entering the blood. And these are formed by really tight junctions from lots of different cells that are together to form a membrane. So this is our membrane. Here is the outside of the membrane. So For example, this is the gut, and these are all different molecules that we've consumed in the diet and that have been broken down into much smaller molecules. So here we have tyrosine, and we can imagine these are all different molecules, for example, carbohydrates, other amino acids. They're all in this kind of soup outside of the membrane. The point is that small molecules like this just simply cannot float across these membranes. They're very tight, it's very regulated. This is the inside of the cell, and through this, different molecules can enter the bloodstream. So we can see here that tyrosine has a dedicated protein transporter. So this is a protein that sits within this layer, and it kind of acts like, we can think of it as a gate. So it will only let certain molecules through. Only certain molecules, fit the geometry. So some molecules are kept out, others are let in, and there are many different transporters dedicated to different molecules. So we can see here that our tyrosine transporter has allowed one tyrosine molecule through. The way it works with tyrosine is it's co-transported with another molecule, a sodium ion. This transporter undergoes a conformational change that enables the tyrosine to sit within this pocket here. And then it undergoes another change where the tyrosine is released and it's free to enter the cell and then enter the bloodstream. And all of this happens really, really quickly, so less than milliseconds, and there's many of these transporters right across the linings of the kidney and the gut. So it's a really rapid process, and some of the work that Juliet has done on tyrosine absorption in the mouse model shows just how fast this happens. So when we consume a protein-rich meal, I think in the mouse model within an hour and a half, most of the tyrosine had absorbed within that period. So we've kind of mentioned various, in previous workshops, other strategies that we've looked into for dealing with tyrosine, for example, tyrosine binding molecules, different enzymes. And the real challenge is that the absorption of tyrosine is so rapid that it's just a race against the clock. So our idea is if we can take advantage of these transporters, we can come up with different ways to inhibit the function of this, and it will prevent tyrosine from being absorbed, from reabsorbed, and it will mean that instead we're just eliminating it out, whether it's in the urine or the feces. So really I'm interested in how we can take advantage of this biology to come up with future therapies. So in a broader context, biology is just never simple, which keeps us in a job. But there are many, many different transporters. There are actually hundreds of different transporters of this class where they sit within the membranes. And this is just a list of the transporters for different amino acids, of which there are 22. So there are different mechanisms, different molecules that they transport. So there's a whole lot more going on than just our one transporter for tyrosine. So again, things are just never straightforward, and there's a lot more to consider. So when we think of the way these membranes work, what we don't have is a situation where things can just float in and out of cells, in and out of the blood. It'd just be total chaos if that was the case. This is a pitch invasion. This is my team, Tranmere Rovers football team, you might be aware of. We don't really get many opportunities for celebrations at my club, so this was actually an angry protest, and it was the only Google image I could find of a pitch invasion at Tranmere. So thankfully we don't have a chaotic situation like this. What we have is something a lot more orderly. So we can think of amino acid transport as more of an airport where we have regulated systems, we have different gates for different molecules, different gates, different destinations, different things being transported. And this is good news for us because it means that we can look to target specific transporters specifically those that act on tyrosine, and we can use this order to our advantage. So one of the inspiration for this approach to dealing with tyrosine came from patients who were identified who have a mutation in this transporter protein. So the one we're interested in is called 6A19. So it's the major transporter of not just tyrosine, but also other related amino acids, including phenylalanine. And it was identified that so it's really rare to have a mutation in this transporter. And this was the first person that was identified that had this disorder. And really the only effect was there was no serious symptoms. For most patients with this disorder, there's no serious clinical symptoms apart from high excretion of different amino acids in the urine. So and this includes tyrosine and phenylalanine, as we can see here. So this encourages us that if we can target this transporter specifically, it's probably one of the safer ways of dealing with tyrosine without having lots of other negative consequences. So the idea is, can we inhibit the activity of this transporter in order to deal with tyrosinemia? And can this be an alternative to dietary modification? So could it be the case that patients on nitisinone could have more of a normal consumption of protein, and could we just deal with it in other means? So the idea is that we can inhibit the transporter, we prevent or inhibit the absorption and reabsorption of tyrosine, and the effect is that we can instead favour the elimination of this in the faeces and in the urine. And thankfully, so I spent some time in the lab looking at different existing drugs, different kind of screening programs, and the aim was to try and identify some molecules that seem to have activity to block the transporter. And it turned out that pharma was actually ahead of the curve. So we have been in touch with several biotechs and pharma companies who'd already developed some inhibitors of this transporter, which was good news. They were mainly interested in a related condition, PKU. So I mentioned that this same transporter transports phenylalanine. PKU is much more common, so there's a bigger market. So really, we were encouraged, and we thought we could, take advantage of some of this work that's already been done, and could we repurpose some of these molecules for tyrosinemia? So one of the companies that we've worked with in particular has made some really rapid progress in recent years. They've done a large preclinical program where they've identified specific inhibitor molecules for the transporter, and they've actually got to the point where they have a drug in clinical trial. This is a drug that's taken orally twice a day. So really, it's a non-invasive route of delivery. And there's been 2 phases of clinical trials undertaken so far, and the results have been really positive. First of all, there's been no serious adverse effects reported. And secondly, the efficacy data is really encouraging as well. So this is the recent data that they've presented, 2 different doses of the drug, and you can see there was a marked reduction in plasma phenylalanine at 28 days compared with baseline. So you can see it was consistent for all patients. And at the higher dose, the majority of patients were under the target phenylalanine concentration of 600 micromolar. So it seems to be a really encouraging approach. And you can see in the placebo group, which was patients were not on the drug, there was no real change in phenylalanine over the same time. So good news. They have a really catchy tagline, which is P the fee. We're still working on an equivalent one for tyrosinemia, but yeah, we're not there yet. But it's a really simple mechanism where instead of absorbing amino acids, we can eliminate them mostly in the urine. So our question was, do we get a similar effect in tyrosinemia? We had no idea whether this would be the case, although we know the transporter can act on both phenylalanine and tyrosine. So fortunately we have this mouse model of tyrosinemia, so we give the mice nitisinone. They have a reliable increase in plasma tyrosine. And this was work, the actual mouse work was done by the group here in Liverpool, including Juliet. So we have a great team who did all of this work. And we tested a couple of the compounds that have been developed by the pharma companies and the biotechs that we've worked with. So the first study was a very short-term one. It was just over the day. So here we had mice that were started on nitisinone and kept on nitisinone for a week. And as you can see, there was a really reliable increase in plasma tyrosine. These are normal levels that we would expect in mice that have been treated with nitisinone. So this is tyrosinemia. We had a control group. So at this point, we gave the drug by gavage. So we know exactly how much of the drug the mice got. And in the control group, there was a slight decrease in plasma tyrosine across the course of the day. But when we looked at our two different doses of the drug, there was a clear further decrease compared to the control group, which was ranged from 51% to 40% at 1 to 3 hours, and it was maintained over the course of the day as well. So we were encouraged by this. It shows that short term, in principle, it's an effective way to reduce plasma tyrosine. And we think that the main effect is actually in the kidney. So we think that inhibiting the reabsorption in the kidney is probably the way that this drug is working. You can see just how clear the increase in urine tyrosine is. So the tyrosine that would otherwise be reabsorbed seems to be just eliminated in the urine. So really promising results from this short-term study. But of course we wanted to look beyond just the blood and the urine, and we looked at various different tissues as well and measured the tyrosine in these tissues. And it was really encouraging that over such a short period, we actually got a significant reduction in brain tyrosine, and also tyrosine in muscle and heart as well. So it seems to be having an effect on both tissues and the blood, which was really encouraging. The next step was to do a longer term study. So this is with a slightly different molecule with a different company, but it acts in a similar way. And here we had mice that were on the drug for 12 weeks in total. Here the drug was given in a slightly different way, so it was just incorporated into the diet. So the mice were constantly taking the drug every time they ate. We had a control group where the mice were just on a normal diet, so this enabled us to compare across the different groups. And we took plasma and urine at various different time points throughout the study, and tissues at the end. And as we can see, this is the full data, so plasma tyrosine on the left. This is the untreated group, so these mice were on nitisinone. So this is the tyrosinemia level that we would usually expect and that we got. And we had a clear reduction that was sustained right across the 12 weeks at both doses of the drug. And there was a slight dose response as well. So we showed that the inhibition and the effect on tyrosine that we saw in the short term was maintained over repeated dosing over a much longer period. And the urine data matches up with what we saw in the short-term study as well, marked excretion of tyrosine in the urine. The next step was to look at the phenylalanine, so we know that phenylalanine is transported as well. Really, we wanted a minimal effect on phenylalanine. We wanted more of an effect on tyrosine without affecting phenylalanine so much. And this also seemed to be the case, so there was no clear reduction in plasma phenylalanine. So we seem to have some specificity for tyrosine, which is good news. this is the final slide. So this is the brain tyrosine measurements in the long-term study. And you can see this is the control group where we have high tyrosine in the brain on nitisinone. In the two drug-treated groups, there was a clear reduction. These are the groups that were off nitisinone. So you can see we've not brought it down quite to the level of mice that were off nitisinone, but really there's a significant reduction that we think is encouraging. And when we look at phenylalanine, no clear effect across the different groups. So this is good news. I do want to finish by saying we're at the point where we're trying to secure funds to do a more comprehensive research program, try different types of administration and different contexts where we can manipulate the diet and see the effects. But still, we're at the preclinical phase of this research, so we're not sure exactly how this would be. We're not sure of the full potential of this approach. We think it's really encouraging, but we're not entirely sure of how it would work in clinical practice just yet. There's a lot more research to be done before we're at that point. And I'd just like to finish by giving a few acknowledgements to the wider group here in Liverpool. All of this work wouldn't be possible without funding from the AKU Society and also the huge team effort by lots of people with different areas of expertise. So thank you. And thanks for listening. Happy to take any questions.
Hello, my name is Emer Higgins and I am one of the metabolic and ketogenic specialists at Nutricia. It has been wonderful to meet so many of you over the last day or so and have really interesting conversations on the stands and hear all about your experiences with this condition in lots of different countries. Both myself and my colleagues have been really interested to hear all about your experiences and what kind of resources you have or have not in your individual countries. So for us, it's been really eye-opening to see if there is anything else we can do as a company to support you or to develop certain resources that might be helpful going forward. So if you do have feedback on anything like that, we're always really happy to hear it and share any UK resources we have that might be useful for you as well. So I'm going to talk to you a little bit about Nutricia and who we are and what we stand for and what kind of products and resources we have that might be beneficial to you guys. So a little bit about Nutricia first. So it was all started back in 1896. So we have been around for quite a long time. And that was when Professor Buckhouse patented an infant formula that was easily digestible for infants who are unable to breastfeed. Obviously, that was kind of us finding our purpose as a company, and it consequently saved the lives of thousands of babies around the world at that time. Then in 1901, the name Nutricia was founded, which actually comes from the Latin term to nurture or to feed, so quite appropriate for a nutrition company. And then in 1946, our first research facilities were established in the Netherlands, which is a really pivotal point for us because obviously research is at the heart of all our products and resources and continues to be a really important part of our company to this day. In 1986, we introduced our consumer care line in order to support healthcare professionals and patients that are using our products and to support them in the usage and answer any questions they may have. Again, this is something that continues to this day to support any patients or healthcare professionals with our products and services. So in 2021, we celebrated our 125th anniversary, which was a really nice milestone for us to celebrate all that we've achieved over that time period. I don't have a more updated slide, but we're now on 128 years. So again, hopefully we'll have many more milestones to come in terms of impacting positively on the world of nutrition around globally. So in terms of Nutricia Metabolics, which is kind of a subsection of the Nutricia company, we continue to innovate and extend our global portfolio of products, and we now actually provide products that helps the management of nutritional inherited metabolic disorders for over 54 conditions globally. So you'll see a range of a few conditions there that you might have heard of. I know there's lots of talk about PKU and tyrosinemia. So obviously we've got a lot of those products, but there's also a lot of conditions that aren't on that slide that we also provide products that help with the nutritional management of it. So that brings me nicely on to our products. So I think we've had lots of conversations on the stands, and lots of you have been very willing to try all the products, which is fantastic. We have lots of different products. Obviously, we've kind of highlighted the 3 that might kind of come into your treatment plan at some point. Obviously, there are differences between countries. I think we've had quite lots of discussions about what's available in different countries and what isn't. So if you do have specific questions, please don't hesitate to ask. So I will look at our TYR GM Pro Mix-In, our TYR Low Flex, and our TYR Low Flex Powder. And I'll look at each of them in a bit more detail, just to kind of explain the differences of what they each are. So with our GM Pro Mix-In, again, I get asked quite a lot what GMP is. So GMP stands for glycomacropeptide, and it was actually discovered, I think quite accidentally, as a byproduct of the cheese making process. So it's naturally occurring protein from a whole protein source. So it's naturally low in phenylalanine and tyrosine, so it was obviously quite a good candidate to then create these very, very low tyrosine products that provide all the other nutrients in terms of amino acids that a patient might need. So they're a little bit different from the traditional amino acid broken down protein substitutes that have been around for a little bit longer. This particular product is completely flavourless and odourless, so it's designed to be kind of fit in with whatever you guys normally take in terms of food, drinks, and that kind of thing. Each sachet is 10 grams of protein equivalent, and it's very low in calories, so there's only 40 calories per 10 grams protein. This particular product doesn't contain vitamins and minerals to allow kind of a bit more flexibility, because a lot of you might not need to take vitamins and minerals, but also to kind of fit in with your lifestyle. And it's suitable from 3 years of age, so obviously for all the adult population it is appropriate. So obviously they come in individual sachets, so obviously that's nice and transportable if you're on the go. Lots of people do add it into food and drink because it does just add in quite nicely and doesn't change the flavour of things. As I mentioned, there is no vitamins and minerals in it, but if you did need to take that, we do actually do vitamin and mineral supplementation, such as our Flexivit range and our Pediatric Ceravit also, that can be used alongside it if needed. What I also forgot to say at the start of this, any of these products tend to be recommended by your dietitian or healthcare professional. They're all prescribable here in the UK, but it's usually on the advice of your dietitian as to whether you need to take these particular products. So in terms of making up GM Pro Mix-In, so we've had some made up on the stand, and lots of you have tried it. So we tend to mix it with about 180 mils of water. We pour in the sachet, give it a good shake, and then drink it. So we've made it up with orange juice yesterday. I think lots of you tried it there. And the idea is you can add it into anything that you enjoy, really. The only thing we say is not to add it into really hot foods above 55 degrees, and that's the same with all GMP products, just because it can change the taste a little bit. So obviously you can add it into other protein substitutes if you're taking more than one. You can add it into the foods you enjoy, so if you take low protein yogurts or foods, or into sauces and things like that. The only thing we say is if you add it into food, to make sure you finish it all so you're getting all the goodness that it provides. A lot of people enjoy putting it into the drinks, so whether it's an iced coffee, whether it's a fruit cordial, squash, water, anything like that, so it can just be added into your normal fluid intake. And then we've got our TYR Low Flex LQ, which is our ready-made product, so that comes in a pouch. And it comes in 2 different sizes. So one provides 10 grams of protein and the other provides 20 grams of protein, obviously without the tyrosine in there. So it's very small volumes. So our 10 grams only 62.5 mils. And then the 20 gram is about 125 mils. So really small amounts to get in that kind of those amino acids. It also contains DHA, which is an omega-3 fatty acid, which has sometimes been shown to be low in people with protein-controlled diets. So again, just an important thing to add in there. It contains vitamins and minerals, this one, so it's got all those nutrients in there contained. And again, it's suitable for from 4 years plus for the adult population. And it does come in a juicy berry flavours. Then we've got our TYR Low Flex powder. So this is another powdered product, but this is amino acid based compared to, say, the GMP one. It can be made into a really low volume, so it's really nice for people who just want to take their protein substitute nice and quickly. It contains DHA, again, that omega-3 fatty acid, and it also has the vitamins and minerals in there. It's a completely unflavoured product as well. It's low in calories. It's got 98 calories per sachet, and each sachet is the equivalent of 20 grams of protein. And again, without the tyrosine. You can also use our flavour sachets. So we've got different flavour sachets to help flavour it if you want to just kind of not have it unflavoured. So we've got cherry vanilla, grapefruit and lemon lime. And then we've got other ones in orange and blackcurrant as well. So again, you can flavour it as you wish. You can add it into other foods. People just like it unflavoured. It's whatever kind of works for you individually. So this is just examples of how some people take it. So some people will just mix it with literally 5 mils of water in a paste and take it that way. Some people prefer to add a little bit more fluid and take it as a little shot. And then some people would like to add the full kind of 65 mils and have it as a drink. So it's still very small volumes and quite quick to take. We do have other little pouches, our squiz pouches at the bottom there. So we kind of provide those as well. So if you want to make it up at the start of the day and take it with you on the go, the reusable pouches to kind of to put your protein substitute in. Then moving on to our products. So I know here in the UK, I think Claire doesn't tend to use too much or doesn't have the need for too many of the low protein products, but I know lots of you have mentioned on the stand that you do use them in different countries. So I thought it was important to tell you about what products we have. So we have lots of low protein pastas. We've got everything from lasagna sheets to macaroni to spaghetti and penne. We've got 3 different types of breakfast cereals, kind of chocolate flakes, strawberry flakes and low protein loops. We've got egg replacers, cake mixes, we've got 2 different types of crackers for snacks, low protein milks, a low protein rice, and an all-purpose mix which we use for things like pizza bases, bread rolls, focaccia, anything you want to make really with it. So that's kind of our range of low protein foods. We also have a recipe book which you may have seen, and we've also got a QR code if anyone wants to download that, and that's just nice for some inspiration for some low protein recipes. It has been designed with all low protein diets in mind, so it will talk about exchanges and things like that, but it will also tell you the total amount of protein per recipe and per serving. So hopefully that will be useful if you want to add in your own exchanges and things like that. And then here in the UK, we have our home delivery service called Homeward. So that is a free home delivery service we offer for all patients who are on our products. And the idea is that they get a free delivery once a month of all their products they have on prescription with us. There's no contract tie-in, so they can come on and off it as they need to. They have a dedicated coordinator, so within the Metabolic Homeward service, it's quite an intimate team. There's only a handful of coordinators, so our patients really get to know us and our coordinators well when they do the monthly stock checks and check that they've got everything okay. We've got our in-house pharmacy and we've got our own delivery drivers as well, and we tend to keep people updated as to when their delivery is due, when they should expect it, just for that peace of mind that they know what's coming. Obviously it might be different, the service that's offered in different countries, but again, if you want to know more about what's available in your countries, please do just ask me or my colleagues, and we'd be happy to look at. We might not have all the information to hand, but we can take your details and get back to you if there is anything that's useful to know. So yes, we've got lots of different resources online, so hopefully you would all be able to access any of our information on our website. So if you go on to the Nutricia website, obviously if you put .co.uk, you'll get all our UK resources too. We also have quite a high presence on social media, so we have our Instagram page, Facebook, Twitter, or actually I think it's X now, and YouTube. So again, there's lots of resources on there, from low protein recipes from our specialist chef, or just hints and tips for traveling, meal ideas, snack ideas, and things like that. And again, a lot of it will be transferable to you guys, kind of in a controlled protein diet. So yes, and if there is any tools that you would like to access or that you don't feel are available in your country, please do get in touch and we'll see if we can share those among you to kind of help with that support. And that is it. Is there any questions or anything anyone would like to know? think I'm getting off easy there. I'll take it.
Great, thank you. Great, so that's it for this session. So we'll be back at 11. So a little break now. Thank you very much.
Thank you.
Hi there everyone, I think we'll make a start. I think most people are here. Can you hear me all right? Yeah, that's all right, just because I'm quite little. You're on tiptoes. So welcome. It's great to actually get the families together. There are one or two families that are missing today, but because everything's being recorded, hopefully we can share that with them anyway. So firstly, I'll introduce myself. My name's Jess. I am one of the trustees for the AKU Society, and I've got a 14-year-old son that has AKU. I don't really need to speak too much about myself because we've got two brilliant speakers that are here today. We have Professor Rankanath, who will be looking at basically alkaptonuria with a focus on children and research so far. We also have Claire, who I think everybody saw Claire present yesterday. So Claire's the senior dietitian for the NAC, and the team are all over there. Claire will be talking about AKU, nitisinone and diet. And again, it's with a focus really on young people transitioning into nitisinone. I know that lots of you will have plenty of questions, so I think what we'll do in both, we will have Ranga's presentation first and we'll have a Q&A session. And then after Claire's, again, we'll have another Q&A session. Some of the questions might blur, and that's fine. We've got plenty of time. Also, what I would like to do, depending on time, I've got a questionnaire that we've created. And the questionnaire is, it's very self-explanatory, and it should really only take about 10 minutes to complete. And it's about, what we're looking at is your experience of the diagnosis of your child with alkaptonuria, from diagnosis through to the kind of resources that you've used, information and advice that you were given, and then with that information, what we hope to do is, because one thing that we did realise, or I realised, that there is definitely a gap in information for parents or young people with AKU. So what we want to do is create a page within the AKU website that is specific to families and young people wanting to get more information. So the information that you provide will help shape the information that we can then provide to future families that receive that AKU diagnosis. So I'll hand those questionnaires out at the end. If we do run over, I'll ask you just to complete them during your lunch, and then I'll walk around and grab them all. So yes, so without further ado, I'll introduce Ranga.
Morning, everyone. I think I see a lot of familiar faces, but I'm also seeing some new faces which I haven't seen before. Hi. So let me see how this works. Yeah, that's so. The focus of this presentation really is to talk about what we know about alkaptonuria in children. I think we've learned quite a lot about alkaptonuria in adults since 1998, really, when the NIH study got going, and we got going in 2003. So we've learned an awful lot. We now have a treatment for alkaptonuria, which is nitisinone in adults. The question is, it's only for adults. So what do we do about children? The question, what do we know about AKU in children? So these are the kind of things I'm going to be addressing. Because I don't want to mislead, I'm going to present facts, okay, and then my interpretation of the facts, which is open to debate. So there's a fair bit of science in there, so I hope you don't mind. I think after a day and a bit, all of you know what alkaptonuria really is. It's the lack of an enzyme, Homogen said 1,2-dioxygenase, which means you can't break down the protein that you ate yesterday. All the protein that you eat, all the protein I ate yesterday has been fully metabolized. And I'm now ready for protein again today. Because you can't store protein, you have to use it or you have to break it down. And the only way we can break down the phenylalanine and tyrosine that you consume in the diet is through this pathway. And of course, in alkaptonuria, the problem is we don't have this enzyme, so therefore you can't break down homogeneous acid, and it accumulates. I think it's important to point out, in view of this presentation, that alkaptonuria is present from birth. Okay, so people are born with the condition. So that is something to remember in the context of this presentation. The kidneys are real heroes for people with alkaptonuria because they are fantastic at getting rid of homogeneous gas in the urine. The concentration is about 1,000 times greater in the urine compared to the blood. Okay. Despite that, the homogeneous gas in the blood still goes up and starts to become deposited in various tissues in the body, including the cartilage, the tendons, and other tissues. And of course, they also cause pigmentation when they go into the tissues. And the pigmented tissues, it's not just an interesting color, the nature of the tissues change. They become stiff and brittle and break down. And of course, it's that breakdown which is the cause of all the problems in terms of the morbidity of alkaptonuria. Okay, so I'm sorry that's moved. The damage should be on this side. This is what happens when you come to a nice new place when you try it on a new computer. There are other features of the condition, so which is shown on this slide. So in brackets are features of features in those without AKU. For example, aortic stenosis in the general population without AKU is 3%, is 23% in those with AKU. Okay. Think about kidney stones, it's 10% in the general population, 25% in those with AKU. Joint replacement, 3-fold increased. Rupture, 75-fold increase. Okay. So all of this is because of the pigmentation process in alkaptonuria, and all of this starts here from a very early age. Or does it? So we try to examine how the pigmentation process develops, because that's crucial for us in terms of thinking about children and how they evolve. Of course, we can't do this in children, so we resort to looking at mice and of course, we have AKU mice in the University of Liverpool. I'm sure my colleagues here were talking about this today, and no prizes for guessing which one has AKU. Yes? Yeah, this is the one with AKU. The bedding is black because of the urine. Okay. And of course, the plasma homogeneous gas is 3 to 4 times higher in mice with AKU compared to humans. So it's quite high. Despite that, for reasons we don't fully understand, they don't pigment as much as in humans. And it would be fantastic. I made a joke the other day to say if we could turn humans to mice, then we wouldn't have an AKU problem, because there wouldn't be joint replacements or anything else. So if we could understand why the mice don't develop, AKU mice don't develop pigmentation, I think it would be a fantastic thing. Okay. Now, when you look at the mice here, these mice, the knee pigmentation increased progressively after a slight delay throughout their lifespan. Okay. Now, when we gave nitisinone, which decreases homogeneous acid to these mice, after the pigment has started, then what happens is the pigment, instead of increasing, stays the same. So the pigment process is arrested. So which is good news for people with established AKU, which means we can control it, we can slow it down, we can stop its progression. Okay. And we also started nitisinone in these mice soon after birth. And of course, when we did that, the pigment never appeared. Okay. So that is the basis on which we have to think about children and alkaptonuria here. That's what we're doing. Okay? I'm not saying we should give nitisinone to children yet, but there's a question, should we? Okay? Now, this is the very first natural history study, in other words, the evolution of human alkaptonuria, the clinical features. And this was published, as you can see, in 2011. At the time, what we saw was that the features of AKU began by age 25 and kept increasing. Okay? So, we didn't know what was happening before the disease became overt. Okay, so but we thought that the pigmentation process must be happening from birth, even though we couldn't see it in a sub-threshold fashion. Okay. So at the time when we started, we said, okay, AKU takes hold of 25, so yeah, we can wait until 25 before we can really think about starting nitisinone. That was the thinking in 2011. Then we did a study funded by the European Commission called SOFIA. The SOFIA, we extended the age to 16. We went down because in the first study, our youngest was early 20s. Okay, so we went down to 16 now. And you can see here, this is a cross-sectional study. We did ear biopsy, gait analysis, and questionnaire, and we had 30 patients, still small, age 16 to 20, 21 to 25, and we had 4 patients. We tried to get 4 patients in each group. Okay? There were 7 patients younger than 25 in this. And what we found was all age groups had AKU, abnormal gait, and an AKU score, which means AKU is burden of disease. That means the clinical features of the disease were already present, even by age 16. Okay? So we concluded that alkaptonuria and pigmentation, the clinical features, could be present before age 20. Okay, so you can see already in the gap of 8 years, we've come down from 25 to less than 20. Okay? Now, one of the key questions is, should we worry? Because if alkaptonuria is reversible, there's no harm in starting later, because you can just reverse it if they come later. So the question is are the features reversible? And we looked at that. So what you see here is 3 patients, A, B, and C. And they came in 2012 when the National Alkaptonuria Centre was set up in Liverpool. That was the first visit to the National Centre. But these 3 patients also came 3 years before for a research visit. So we had photographs to compare. And what we saw was in the 3 years, these things never look as good on these screens, but believe me that there's an increase in pigmentation in all 3 from pre to 2012 when they came to the National Centre. And then they started nitisinone in 2012. And then we have been taking pictures annually to see how they progress. And what we found is 3 years later, the pigmentation is clearing up. Okay, in fact, the pigmentation is less than it was 3 years before they came. Okay, so, but it's still there. It hasn't gone away fully. So although it is partially reversible, it's not fully reversible. Okay, so there is residual disease. And I'll come back to this again. So before you can treat something, you need facts. You need to understand it. Okay, so what I've tried to do in the last 2 years or so, when we wanted to go with a proposal, myself and Nick, we wanted to go to Swedish Orphan Biovitrum and ask them to support a study of nitisinone in children. Okay, to do that, we had to put a case together. So I've come with a proposal, which means I had to educate myself to see what we knew about children. So when I looked at all the published cases of children with AKU, I found 49 cases, 9 under the age of 1, 14, 2 to 5 years of age, 19 cases between 6 and 10, and 7 cases more than 11 years and less than 18. Okay, and of course, many of the children had pigmentation, 4% had joint pain. There were 2 larger publications from Turkey, but they didn't give great quality data for me to classify those in terms of pigment and joint pain. Although they said there was ochronosis, in other words, pigmentation and joint pain in the patients. These are children, don't forget. Similarly, there was a Dutch series of 12 patients as well. They said there was joint pain and pigment features in children. But again, there's no detailed description of what went on there. So this to me suggested that irreversible features of alkaptonuria could be present in children already. Okay. Now, don't know whether you can see that. It's changed color. I think it's an RGB issue. There are two important studies I just want to mention. One is a study in Slovakia. Slovakia has got the highest frequency of alkaptonuria in Europe. Okay, it's about 1 in 21,000, something like that. And what Serson and colleagues did in 1982 was they actually published more. They went up to over 65, but I have reduced that so that you see only the less than 20 here for the purpose of this discussion. And what you see here is they looked at these various age groups in terms of black urine, earwax, axillary pigmentation, ear cartilage pigmentation, eye pigmentation, and joint involvement. And what they found was they didn't find any joint, they didn't describe any joint issues here, and they didn't state how many children there were of the 114, which is a bit disappointing there. Okay, so this was a Slovakian journal, so the standards of journalistic rigor seem to be a little bit less. They would have thrown my paper out if I had written something like this without clarifying more. But in any case, that's what they said. So you can see they found ear pigmentation in a 12-year-old and eye pigmentation in a 13-year-old. So you can get pigment there. The same group also published a different paper where they looked at kidney stones in children with AKU. Okay, these children. And of course, what they looked at here was 21 children, 10 men, 10 males, 11 females, and they had 5 of them had stones, either by ultrasound or they passed stones. Okay, and they had they also looked at ultrasound and non-AKU controls. And there were 2,382 and they had 5 stones. So the frequency of that in AKU is 23.8 versus 0.2% in terms of the frequency of stones. It's very similar to the data I showed you in adults with alkaptonuria, the stones. It's 25% that I showed you in our NAC. So this seems to be fairly similar. This is an important study because this was carried out much more recently. In 2023, this was published. And they looked at all the children with AKU that they had in Poland. And this is the clinical data in this group. So what you see there is there were males and females. And I put it in ascending order of age. And it goes from 4 to 17. And you also see that the dark ear wax was present even early. Okay, it's not necessarily an age-related thing, and that's because in the secretion and the wax you can get homogenic acid. And the sweat contains homogenic acid, by the way. Okay, and one of the intriguing things I see when I see patients back the first time is when they came back the first time, and the first visit back on Nitisinone, they all look bright. Okay, that's because the skin homogenic acid is gone. They all look great. And it's the same here. So this doesn't mean that much. And of course, what they found was they found scleral pigmentation in 3 patients. They also found ear cartilage pigmentation as well, and skin pigmentation. And more important, they found joint pains, okay, in 40.6% of the time. When these children came to the clinic, and it was higher than matched controls without AKU that they saw in the clinic. So the other important thing for me is all of these features, especially the pain and the pigmentation, were after the age of 10. Okay, so are very evidence-driven. So I won't do things because I want to. I want to do things based on what we see. So at the moment, I think we can go down to age 10 and say, look, they're having joint pains already. So the question is, are they having joint pains because they have changes in the joint, because they've got pigment, early pigment, and therefore we need to understand that better. The other major thing that the Polish group did, they must have done this because their children were needing psychological support, okay, AKU children. And what they came with, the 5 of the 13 children needed psychological support. In other words, they were saying 5 of the children had learning difficulties. So cognition was impaired in AKU. Those are the facts that we have from children so far. Okay. When I looked at that, I said, if these changes are happening in children already, surely we must see them in the youngest adult group that we see in the National Centre. So I started looking at the young adult group, and I'm just going to share the data here. So this is the metabolic and clinical data from the youngest group, okay, under the age of 25. And what you see there is different ages, okay? So I'll just point here. So this is the mean age of 19.3 females, 7 males, 4 with eye pigment, nobody with ear pigment, skin pigment in 1, back pain in 8, joint pain in 3. All this was at baseline, mind you. This is what I'm saying. I'm not talking about as they're getting older. So this is all at baseline. So for me, this is suggesting that, yes, the childhood thing is believable, okay, because we're seeing it in the youngest adult group here as well. One of the things we do, thanks to Professor Barton sitting there, is that all our patients coming to the NAC undergo clinical gait analysis. So if you've got pigment in the cartilage in the joints, they become stiffened, and therefore your gait changes. So if children are getting joint pains, I ask the question, is it because they also have pigment in the joints, and do they walk normally? Okay, and of course, I'm just going to point you here to these 2 columns. So this is the mean of those 10 adults, young adults. The mean score was, and this is the non-AKU reference range. Okay, so this is the AKU group, this is the non-AKU group. Okay, and we looked at, I've shown you 3 things here. One is the number of steps per minute that they can walk. How long is the stride? And how fast can they walk? Okay, so if your cartilage is stiffened, these could be affected. And of course, what we found was the number of steps doesn't, the cadence is not really affected that much. It's more or less the same as, but both of these are in the lower third, is what we call the tertile, okay? They're in the lower 1/3 of the non-AKU group. So it does look, and I know Gabor may have something to say about this later, it does look as though the young adult group has got gait issues already. The other thing we do, when we started the National Centre, of course, it was we had no idea what was going to happen with high tyrosine when we started Nitisinone, because we were hearing mutterings in 2011, 2012, that cognition could be impaired if the tyrosine goes up after Nitisinone. So when I set the National Centre up in 2012, we put in psychometry testing as routine. Okay, so all our patients have psychometric testing at baseline, and then they have it once a year. Okay, this is to make sure that we're not harming our patients. Okay, so when you look at this younger stage group using what's called the Wechsler Adult Intelligence Scale, these are the scores, these are IQ scores really, and what you're seeing there is comprehension index, reasoning index, memory, and processing speed. Okay, these are all different facets of our thinking. Okay, and when we do that, what you should have, the normal score is 100. Okay, And 2 standard deviations below that is below the reference range. And the standard deviation there is 15. So 100 minus 30 is 70. So if the scores are less than 70, they're not okay. And this is what we found at baseline in these young adults. Okay? And you can see that. The other amazing thing, which we didn't expect, is they have these psychometric testing every year. They're administered the same questions every year. Okay. And what you see there is that baseline 1 year, 2, 3, 4, 5, 6, and so on. You can see the comprehension score has gone up. So there's everybody, it's not just the young group now anymore. Reasoning score is going up. Memory is going up. Speed is going up. So one way of interpreting this data is to say, well, it's just a learning thing. We're administering the same questionnaire. They're just getting better at it. I mean, it's a year's gap. I am not sure I would remember in detail all the questions I was asked in psychometry a year later, and I don't think you're going to get an overall increase in scores like that. So we should be open to the idea that decreasing the homogenic acid by nitisinone may improve the psychometry scores. If I just take a step back, I didn't emphasize this. The Polish study suggested that there is cognition issues, and the National Cap Center, the baseline suggested that scores are low. So therefore, it begs the question, is homogenic acid responsible for that? Very important question. Okay? Because if it is, then decreasing the homogenic acid might be beneficial. Okay? We tested this. Okay? We had a PhD student called Roisin Lewis. She's a doctor now. She's a doctor, because she's also a medical doctor now, not just a PhD doctor. And what she did was she tried to understand the effect of tyrosine in mice. That's what she did. That was a thesis. She's uploaded a thesis, by the way. It's on the internet, if anybody wants to go and have a look. And but what she did was something called the Morris water maze. Okay, so she was testing the mice to see whether they could learn. Okay, and what she did in this maze, you can see there's a mouse there. Okay, so if you insert the mouse there, they need to find this hidden platform so that they can get on it and stop swimming. Okay, and all the mice were trained initially, and then there was a trial to see whether they could remember. Okay? Her conclusion, 3 conclusions. The first conclusion was she said, wild-type mice, I've changed that to non-AKU mice for those of you who don't understand what wild-type means. Okay, that means non-AKU mouse showed significant improvements in performance throughout the hidden trials, with the probe trial confirming they were able to form and recall spatial memory and utilize this for navigation. In other words, they could find the hidden platform very well. Okay? Then she talked about the HGD null mice. So I'm going to change that to AKU mice. That's what HGD null is. Okay? These are AKU mice, she said, showed minimal improvement throughout hidden trials and showed no preference to any quadrant, target quadrant during the trial. So it's an important finding. It's maybe an indication that they're less able to use the hippocampal dependent learning for navigation and so on. So basically they're saying they don't learn well. Okay, just okay. Important conclusion. But one more, because she also gave nitisinone to these mice. Okay, so the nitisinone is given both to AKU mice, in other words, decreases the homogenic acid, but also increases tyrosine, and normal mice, which don't have high homogenic acid, but the tyrosine goes up after nitisinone. And what she found was the treatment had no effect on the performance. Okay, so there were no indications that treatment was detrimental. In fact, the scores improved in the AKU mice that was given nitisinone. So I've just summarized this little bit because it's quite important for us to understand that we don't do any harm. So the Polish study says children with AKU have learning difficulties. Young adult NAC groups, psychometric scores lower at baseline. So all NAC patients show apparent improvement in psychometric scores with nitisinone, and the AKU mice show impaired performance and improve with nitisinone. These are the conclusions here. These are the findings. How we interpret them is up to us. So when you're thinking about starting treatment, there are some new data, new knowledge that we've understood, which is due to lifelong exposure to homogentic acid. Okay? So, and these are, as you can see, cataracts are more common in AKU patients. We also found 20-fold increase in Parkinson's disease, both before and during nitisinone, and I'll come to that. Underactive thyroid and thyroid tumors are also higher in those with AKU. And we think all of this is due to the nature of the homogeneous gas, which is an oxidant. Okay, it causes oxidant stress. And if you don't treat children, then you've got 16 plus years of homogenous acid exposure that is contributing to these features that come on later on in life. If you're able to reduce the duration of homogenous acid elevation, that much oxidant stress is decreased. Okay? Nitisinone is an imperfect treatment. Why do I say that? Well, we know that it is very good in terms of decreasing the homogenous acid, but the problem is now the phenylalanine and tyrosine has nowhere else to go. Okay, so you get high tyrosine. Okay, and the high tyrosine is problematic as well. Okay, and I know you've probably heard from Brendan and Juliet already, but I will just present one slide on what it is in a minute. Nitisinone is very good for AKU because it is proven to lower homogenous acid in the blood at 10 milligrams, 99.7% decrease. I've not seen anything in medicine as dramatic as that in all my years of practice. Okay. It also partially reverses the pigment. I've showed you the photos and we've confirmed that in clinical trials again and again and again. Okay. In people blinded to what was done. And it slows the disease. We've seen that. Patients more comfortable, less pain, walk better, all kinds of things. So it's a no-brainer, really. The alkaptonuria is improved by AKU, by nitisinone. But we don't want this high tyrosine. Okay, what does it do if the normal level of tyrosine is less than 100? So if you go on nitisinone, it's going to go up. If it goes up more than 900, you're going to get deposition of the tyrosine in the cornea and cause a conjunctivitis like a red eye syndrome. Okay, and because it's painful, you won't ignore it. And then if you stop it, it's reversible. Within a few days, it goes away, and then you restart a month later after full recovery, if you like, and healing with a more restricted diet, and you're fine. And that's what we do in the National Centre. The other thing we see is vitiligo. So this is vitiligo in a patient who was perfectly normal before, at baseline, coming to the National Centre. Okay, his family had underactive thyroid and SLE, so there was a strong autoimmune diathesis in the family, which means he and they probably had subclinical damage to the melanocyte. They must have had antibodies to the pigment-producing cells in the skin. And of course, once they go on nitisinone, the high tyrosine seems to just unmask that, makes it faster. The problem is it's irreversible. Okay, so you can't do anything about him, by the way. So he has the option of either stopping and the skin pigmentation isn't going to change, or allow the disease to get worse. Okay, so so I warn people, especially those with a history, personal history or a family history of autoimmune diathesis, to say this might happen, and then they can decide whether they want to go on it or not. Okay? One of the major issues is the dietetic thing. They need to be on a low-protein diet. Okay? Because you want to manage the tyrosine. You don't want it going too high. Of course, that means patients with alkaptonuria at baseline are malnourished because of a long history of diet change, and I'll come to that in a second. So therefore, and because they're also now on a restricted protein, the muscle mass doesn't improve, so which is not great. And of course, there's also the social issues, the isolation, because you're not allowed to eat with peers in terms of food and all the rest of it. So these are all the undesirable things. Remember, I said the cataract, the Parkinson's can also occur during nitisinone treatment. And I think that's just follow-up because of the lifelong exposure to homogenic acid. It's just the addition of tyrosine on top of that. Maybe it doesn't just change, it happened anyway, or maybe there's a small contribution from the tyrosine to the cataract. So in the University of Liverpool, when we've done studies, we found that homogenic acid is much more important in terms of the cataract in mice, in lens in vitro, okay, when we do the experiments, than tyrosine. Okay? And of course, Parkinson's disease occurs due to oxidant stress over a lifetime. And of course, there are some interesting biochemical reasons as to why high tyrosine can inhibit dopamine formation, which is the problem in Parkinson's disease. And again, that is because of the pre-existing homogenic acid-based oxidant stress killing off the substantia nigra cells, which leads to Parkinson's. Okay, so I don't think tyrosine itself is that much of a culprit. So I guess I'm arguing, if the homogenic acid had been normal and the substantia nigra cells didn't die off as much as in normal people, then nitisinone might not have caused unmasked Parkinson's disease. Anyway, I'll stop hypothesizing there. So when we started developing nitisinone, we didn't want to go into children because there was this concern due to experience with hereditary tyrosinemia type 1. Hereditary tyrosinemia type 1, for those who don't know, is a nasty inherited metabolic condition in children where they die within the age of 2 due to liver cancer and liver failure. Okay? And the nitisinone therapy is life-saving because it blocks the pathway and stops the toxic metabolites from being produced. But unfortunately, what they found during this time was that many of the children, depending on which one you say, anything from 10% to 50%, developed learning disorders, okay, cognitive impairment, in other words, while they were on nitisinone. Of course, I've looked at the research carefully now. It'll take a whole session to present the evidence here. And the literature now, the latest literature suggests it's not due to the tyrosinemia, it's due to the hereditary tyrosinemia type 1 itself. It's the nasty condition which is causing the cognitive impairment. And that fits in nicely with the psychometric scores apparently increasing when we, in the National Centre in AKU patient illness. So the conclusion there was tyrosine during nitisinone treatment doesn't cause cognitive impairment. That seems to be the evidence at the moment. Very important. When should we think about starting nitisinone in children? Okay. Brain growth. For example, you have to restrict the diet. Okay. And of course, the high tyrosine could decrease the supply of amino acids to the brain. So therefore, you don't want to interfere when the brain is growing too rapidly. Okay, so you want to start a little bit late. I mean, if I was a parent, I would probably, that's what I would want to do. Okay, so, the most important thing in medicine, you'll hear all doctors say, is even if you don't do any good, don't do harm by what you do. Okay, so that's fundamental in terms of what we do. I think if and when we start nitisinone in children, there has to be careful monitoring. So we have to do psychometry testing, slit lamp examinations, or on a regular basis to make sure they're all right. I found this in Smithsonian Institution, by the way, recently. And what is going on here is how fast the brain grows in humans, okay? And this is age. And you can see by age 7, it's more or less flat. The brain growth keeps happening. It keeps maturing until age 25. Of course, we are not going to wait until age 25 to start nitisinone in adults. We want to start earlier. Okay, so it's all about trade-off, which is important. Okay, so my own view, in fact, this whole presentation is my view, by the way, because there's nothing out there about children, is we shouldn't start before the age of 7. I think it should be after that. Preferably age 10 is what I would say, if pushed. So there's a changing calculus in children. Okay, so you've got the homogenic acid issues, which is all the things that I've told you. Irreversible walk is prevented, homogenic acid decrease from childhood, joint and spine disease prevented, AKU phenotype prevented, not lost to follow-up, by the way, important, because a lot of patients that are here will probably remember being diagnosed with alkaptonuria at birth and then not being followed up. They come up 30, 40 years later with established disease, and it's not fully reversible. So that would be avoided if we started sooner, because then the pediatricians will become interested in this condition. Okay, and they will follow up people more closely. Lifelong oxidant stress minimized, cataract prevented, cognitive deficits are likely avoided, due to the AKU itself, which I told you, and of course hypothyroidism likely prevented. And undesirable things as listed there: tyrosinemia, the protein restriction, the keratopathy risk, vitiligo, Parkinson's disease, unmasked cataract. But remember, this is all due to the lifelong homogenic acid as well, and of course protein restriction during brain growth. Okay, this I guess is what many of you will want to know. What do we do now with children? There's no nitisinone. How should we go ahead and do it? So this sort of illustrates the principle of timing nitisinone in childhood or in human age. So if this is lifespan, okay, and you can start nitisinone at point A, X, Y, or Z. A sort of 40, 50s is roughly where we are at in current practice, okay. And if you started there, what we're seeing is, at best, you can arrest the disease. Okay? What that means is that you have that much residual disease. Okay? If you start at point X, you have decreased residual disease. Even less residual disease at Y, and so on. Okay? So that's the reason, I think, why we should think about the timing is important. Okay. The various supportive and preventative therapies that have been touted in childhood. Diet, and I'll come back to that, and vitamin C. Hydration is important because the kidney stones, as I said, is about 25%. Okay, so hydration in children is interesting issue. I've been hitting the internet to see what recommendations would you give for drinking in children, because in adults it's easy. I had a kidney stone 2017, New Year's Day. I was in A&E, and they say, oh, drink 3 liters a day. Of course, I knew I was drinking 600 mL is the urine output at the time. It's pretty awful. So, but it's depending on the age, you might need to think about how much you drink. Okay, it's 900. Less than 10 years, and it's a bit more up to 1,200 with slightly older children. But you'll have to be guided by your pediatricians And it's very important with the kidneys are really crucial for people with AKU. Maintaining an optimal body weight is a good idea because the heavier you are, the more stress on your joints and spine, and the more damage you're going to get. So I think remaining slim is a good idea. Early habits are good because if I have established disease, AKU, and my joints and spine don't work, I'm not going to work out. I'm going to say, blow it, I'm getting a bit bigger, so be it. Okay. So, and these things from childhood are probably quite important. Of course, that leads me on to what sort of physical activity should you do. The NIH came up with a nice study where they said stretching they found in their patients to be beneficial. And that makes sense because the tendons are pigmented, and if you stretch, you're stretching the tendons and making them more pliable, so it allows you to walk better. So maybe that's a good thing to think about. I think contact sports are not a good thing. I'm looking around, I don't see that patient that I look forward to see from Wales. He was a boxer, professional boxer. Guess what happened? Both shoulders replaced first. Okay, so contact sports are not great. You have to think about activity that is safe and sensible. Okay, swimming, water-based activity is good because you're not stressing your joints and spine. I wouldn't quite say yoga. Maybe when you're very young, starting something like that might be a good thing, but not with established AKU. Cycling is good. Walking is good. Water-based, as I said, those are probably the kind of thing that will be beneficial. You have to think about your hobbies, what job you want to go for, because don't try and end up in physically demanding jobs. I know one patient who was a teacher who had to stop working because he couldn't stand in the class. So important to plan ahead. Chondroprotective activities are a good thing. One of the key things is loss to follow up. To minimize that, I think national registration is important. That will allow regular annual follow-ups, and we can surveil for complications that come on with alkaptonuria. I've not heard of any child taking painkillers yet. Okay, so but you can see the joint pains are being described in there. Just touch on diet. Okay, neither vitamin C nor protein was associated with reduction in urine hormone. This is the New England Journal of Medicine study from the NIH. Okay, this is the Liverpool NAC publication. So what we said was 50% reported some degree of protein restriction in the life. AKU patient had lower muscle mass, grip, higher body fat, meet the criteria for clinical malnourished at baseline. Okay, and of course we then put them on continued dietary restriction because we have to manage the tyrosine issue, which isn't great. There's no relationship between protein intake, high dose vitamin C and AKU disease severity. That was the conclusion. This was a paper done by Claire's predecessor, Shirley Jung. We are told, and of course we've got some French people background here, that French patients restrict their diet better. Okay, they're told to restrict better. And I'm told hearsay that the children end up being a little bit smaller in France. So I was quite interested to see whether this worked in the clinical trial that we carried out, because we carried out a clinical trial called Sonia 2. And we had the Liverpool site where the patients were not from the UK, by the way. There were 3 from Northern Ireland, 2 from Wales, and we had a lot of patients from Belgium, Netherlands, Italy, Spain, and so on. Okay, a very small number, couple I think from France, and you've got so Liverpool had 41 patients, Pistani in Slovakia had 65 patients, the most number, and Paris had 32. So we were able to compare to see how they behaved. So the age was more or less the same. Okay, the homogeneous acid levels in the blood and the urine were also very comparable. It's not statistically significant at all. Okay, and important, the burden of disease, the alkaptonuria severity score index was more or less the same. I think the lowest was actually surprisingly Slovakia. I don't know whether they've got some neat trick because they've had the disease for so long, and they know what to do. Just raises the question. Okay, but the French patients were not especially benefited by being on more rigorous protein restriction. I was really interested in this and said, why not? I mean, if homogenic acid comes from protein, which contains phenol and tyrosine, surely you must see some effect of diet. Okay, so at baseline of all patients coming to the NAC, I plotted the plasma homogenic acid against 24-hour urine urea. Let me explain what this urine urea means. So all the protein I ate yesterday, which is basically made up of amino acids, broken down, and the amino groups are converted to urea. And the urea then comes out in the urine, and by measuring the urea in the urine, we have an idea as to how much protein I ate yesterday. Okay? And if you plot the blood homogenic acid against the urea, you should expect to see a nice, beautiful line like this if it's a straight relationship. Okay? If there's no relationship, you should see a flat line. And that's pretty much what we have here. Okay? So we are not seeing a good relationship between dietary protein and homogenic acid. No surprise that low protein diets don't work per se in AKU. Probably means the metabolism of homogenic acid is more important. Nice, lovely kidney stone in a patient on nitisinone, which is why it looks paler, otherwise it's black. And as I mentioned already, hydration is important. People used to take vitamin C, and even though it didn't work. And of course, vitamin C also is responsible for kidney stones, because you're taking high dose vitamin C. You have to ensure that the hydration is good when you're on those. Increasingly these days, vitamin C is an antioxidant. So if homogenic acid is an oxidant, I'm now increasingly thinking, should we be thinking about vitamin C in our patients to minimize cataracts and Parkinson's disease? I don't know, but it's something to think about. Okay, I'm nearly finished now. So where are we now in terms of understanding the evolution of the disease? I'm sorry, I've got run over. Full hour. I told you it was going to be quite factual. So where we are now is, so we think the octanosis, the pigmentation process proceeding all through life. And we now, so these are late features, and we think there are early features now from age 10. And at the moment we think there's not very much happening at less than 10. Okay. Several challenges in thinking about nitisinone treatment in children. Okay, we've had this proposal now for 2 years. Okay, we can't interest a pharma company to come in and help us with that. I know Nick and myself, we've tried really hard to get a pharmaceutical company to come, and they don't want to do that, because if they put in $500,000 to $1 million and get it approved for children, the other generic guys might actually benefit, because there are a lot of generics around now. Okay. And there's an issue of funding. I mean, you know, the European Commission was fantastic for AKU, but that program seems to be gone now. They're funding masses of diseases rather than one disease. I think it would be wonderful to have a mechanism by which we can get some funding to do this. We need $500,000 at least. Okay, I'm wondering whether NIHR might be an idea to go to in that. I think the features are there in children, but they're still soft, and they're not conducive to hard endpoints in clinical trials, so it's going to be metabolic. On the other hand, I could say the SONIA-2 study was the urine homogenic acid. It's a metabolic endpoint, so I don't think it's a major issue. Of course, it has to be multinational, because as far as I know, there are about 15 children with alkaptonuria in the UK, and in Poland they had 13 children. That's all the children there. So it will probably have to be a multinational study to do that. So I'll finish with this last slide. So the features appear to start around 10 years of age. Pigment features are not fully reversible. Earlier treatment is better. New features that we are recognizing is cognitive impairment in children, likely due to homogeneous acid itself. High homogeneous acid children may contribute cataract and Parkinson's disease, which come much later on. Nitisinone-induced tyrosine may not associate with cognitive decline, a major reason why we didn't think about developing nitisinone in children previously. Timing of starting is debatable. I think we will need to open a debate. I'm thinking how we do that. I think maybe we should publish this and then see what happens, see what the comments we get. And the crucial thing is safety should be monitored with that. So I'll just stop there. Thank you.
Any questions?
I've been so thorough, there probably shouldn't be too many questions, which is the reason.
One quick question. The way you understand it is that the rate in non-treated AKU. Hi. So just wondering, the rate in non-treated AKU people, you've clearly said the rate of other diseases like Parkinson, cataracts is much higher. Do we have any data on people that have been on nitisinone? Because I think it's used for other...
Very good point. I didn't say that because we've got 35 years of experience of nitisinone treatment in hereditary tyrosinemia type 1. Okay, the treatment started in 1991, so that's 9 plus 24, so nearly 35 years now.
See,
no, none. No cataracts, no Parkinson's disease, nothing.
Thank you.
Thank you very much, Professor Angana. Just one question. Do you think for children, puberty may have a relationship with the onset or the increase of AKU?
Can you repeat that?
Do you think puberty?
Pigmentation, okay.
No, puberty. Oh, sorry.
Puberty.
Oh, puberty, okay. I haven't seen anything, any change. I don't see those patients anywhere. I see adult patients, so I've no idea. If the Polish study can suddenly find that there's cognition issues, maybe it affects puberty. I have no idea. Do you have any idea?
This is I need the question.
I think this is where the research needs to come in, where we really do need to be looking at young people and children.
They do get underactive thyroid, patients with AKU. In fact, one of the Polish study patients had hypothyroidism. I don't know whether anybody spotted it. And the way it works is to make tyrosine, you need to do what's called iodination of tyrosine. Okay, so you need to add iodine to tyrosine. And of course, if you've got homogeneous acid, you can't do that, so you get hypothyroid. I'd better stop. We want to hear what Claire has got to say.
I think what we'll need to do, we'll move on to the next presentation, and we will be running into lunchtime just a little bit. But anyone can come and find Ranga at lunchtime. But I think if we move on to Claire now, that would be great.